Hello students, hope you all are doing well. Welcome you all to the lecture number 4 of our oscillation series. Previously we already discussed about in lecture number 1 what is simple harmonic motion, wave equation and different properties like displacement, velocity and acceleration of simple harmonic motion. In the second lecture we discussed about what is free vibration, damped vibration, wave equation of damped vibration. In the third lecture also we discussed about how the energy decreases or decay in case of damped vibration due to presence of the opposing force or retarding force. As well as we discuss about two important terms. One is said to be the time constant, which is said to be the relaxation time also, and one more factor as quality factor. If you have not seen those videos, I will put the link in the description box. Please go through that. Already we discussed in the previous lecture that there are three different types of vibration. One is free vibration. Free means from the name you can identify when there is the absence of any retarding medium, when the body is free to move without losing any energy. So if there is no loss of energy, there is no loss of the amplitude or displacement. Similarly, damped vibration means when the body loses some amount of energy, or you can say loses the displacement due to the presence of retarding medium or the opposing force. So that type of vibration is said to be damped vibration. And the third case is here forced vibration. So forced vibration means from the name you can identify when some external force is given. In retarding medium, some opposing force is there. Along with that retarding force, if some external force is given to the body, that is said to be forced vibration. For example, if we consider the simple pendulum case, in simple pendulum case, we move the body from its mean position of rest or the middle point, then to one end, then we leave. Then you can see the body will start vibrating. The body will start moving from one end to other end and gradually comes back to rest. But instead of doing that, if we do some extra work by putting some extra amount of force, for example, we are moving it to one side, then we leave, then the body will start vibrating, the body will move to the other side, again return back to this point. If we are giving some external force here, that type of vibration is said to be forced vibration. That means some external force when applied at a particular interval of time, if some amount of force is given to the body, then the body will vibrate with the influence of that external force. That type of vibration, when external force is given, a periodic force, periodic means already you know that, periodic means when at the equal intervals of time the function or the force is given. That type of force when applied, that type of vibration is said to be forced vibration. In day-to-day life, there are different types of forced vibration. Example, for example, swinging a swing. We are pushing constantly. If one person is swinging, then from behind we are pushing after a particular interval of time. That means we are giving some external force. So that is one example. Similarly, in case of any type of musical instrument like guitar, sitar, where strings are there, we are putting some external force so that music is created, sound wave is created. So for example, train case you consider. While train is moving, all the compartments are vibrating because of the repeated motion of the wheels. Because glass also, during concert you can see, sometimes also you can observe that during high music you can see the windows are start vibrating, glasses are starting vibrating, some glasses also shatter because of the forced vibration, because of the influence of some external periodic force. So today we will discuss about what is forced vibration, what is the wave equation of forced vibration, and also we will find out the wave equation solution. The solution of that wave equation also we will find out for forced vibration. Okay, let's go to the topic then. So here you can see the definition is written. So forced vibration means what? When a body is subjected to an external periodic force. Externally, if a periodic force is given, then that type of vibration is said to be forced vibration. Clear? So in case of forced vibration, initially what happens? For example, simple pendulum case. This is the simplest case you can take. In simple pendulum case, we are moving the body from its mean position. Then we are leaving here. Then the body will go to the other end, again return back, and here we are giving some external force. Clear? So we are moving the body. When it return back to a particular point, we are giving a constant amount of force. But for the first cycle, the external periodic force is absent for a fraction of second. Maybe it lasts for a fraction of second, but for that period of time, the external periodic force is absent in that motion. So initially, in the beginning always the body vibrates with its natural frequency. But ultimately, due to the presence of external periodic force, the body vibrates with the frequency of external periodic force. Now we will find out the wave equation. Here you can see we have to find out the wave equation. To find the wave equation, we have to first consider what are the different forces involved here. Once we get the different forces, we will find out the relation between them. So let's find out that. So one is the restoring force. So restoring force is minus ky. Then the damping force, which is equal to minus bv, or you can write down minus b dy by dt. Again, the inertial force is nothing but mass into acceleration, which is equal to mass, then d square y by dt square, double derivative of displacement. All these forces were also there in the damped vibration case. But one more important force is there, that external periodic force. So that external periodic force, we have written that as external, that is equal to F naught sine Pt. Then what is F naught, what is P, and what is that function? Already we discussed this is as nothing but an external periodic force. Since it is a periodic force, we can express in terms of trigonometric functions. And F naught is nothing but the maximum value of force. Maximum value means the amplitude, that is the maximum value of the force or the amplitude of the force. And P is nothing but here the angular frequency of that external periodic force. Already we have used omega, omega naught. If I have written here omega dash, it may create confusion. For that reason, I have changed that notation to P. This is nothing but the external force angular frequency. Clear? So in equilibrium, what happened? Now in equilibrium, the inertial force is equal to restoring force plus the damping force plus that external force. So F is nothing but m d square y by dt square. Then Fr is nothing but minus ky. Fd is nothing but minus bv, and this is nothing but F naught sine pt. In next part, we will just rearrange this equation. So here you can see, so the wave equation will be m d square y by dt square plus that bv term we can take this side, dy by dt, plus ky term we can take to left hand side, so it will be positive ky equal to that external force sine pt. Now we can divide mass on each term, so this will be d square y by dt square plus b by m dy by dt plus k by m y equal to f naught by m sine pt. Already in damped vibration case, we already know that what is b by m, what is k by m. Here directly we can write down. So the equation will be d square y by dt square plus b by m is 2r, the damping coefficient, dy by dt plus k by m is nothing but omega naught square, the square of natural frequency of the body, equal to, let this is f naught sine pt. So what is f naught again here? F naught is nothing but, you can see this is the ratio between f and m. So capital F naught is nothing but the amplitude of the forced vibration or that external periodic force. So amplitude is nothing but the maximum value, that is a constant quantity. Mass of the object is also a constant quantity. So if we divide that, that is nothing but another constant. So I have just written as F naught. So this equation 1 represents the wave equation of forced vibration, which is nothing but double derivative of y or d square by dt square plus 2r dy by dt plus omega naught square y equal to f naught sine pt. So here you can see this is a second order. This is a second order wave equation and its power 1 means linear. And here the difference is that here you can see the right hand side term is nothing but a different function as that of the y. In damped case, we find out the wave equation in the form of function of y equal to 0. For that reason, we are saying that as a homogeneous equation. But here the function of y is equal to some function of p and t. So it is inhomogeneous or non-homogeneous. homogeneous. So the wave equation of damped vibration was second order linear homogeneous, but what we get here in case of forced was second order linear but inhomogeneous differential equation. Hope you understand up to this. If you have any questions, you can ask me in the comment section. And one more thing, I have given some examples of forced vibration. Whatever the forced vibration examples you face in the day-to-day life, you can share me in the comment section. Now we will find out the solution of this wave equation for forced vibration. So let's find out the solution. We have the wave equation in the form d square y by dt square plus 2r dy by dt plus omega naught square y equal to f naught sine pt. Let it as equation number 1. Let one more thing here you understand that the forced vibration always has two part solution. Its solution is always having two parts. One is for that a short period of time, that damp motion when the external force is not given. That part is said to be the transient part. And the second part, which is under the influence of external periodic force, is said to be the steady part. Steady part. So its solution has two parts. One is the transient part, which lasts for a very short period of time because of that damping case. And when the external force comes into play, that solution is said to be the steady part. So this transient part is due to the equation d square y by dt square plus 2r dy by dt plus omega naught square y equal to 0. Because already I have told you, when the external force is given, before that the body starts vibrates for a fraction of second. That fraction of second, when external force is absent, that part is nothing but the damping case. You must have remembered the damping wave equation, and its solution is nothing but, let we have given as first part means y1 equal to a naught e to the power minus rt sine omega t plus phi. Let it as equation number 2. Equation number 2. So this solution, already we have derived the solution in the damped vibration case. If you don't remember, then you can go through the videos of damped vibration. I will put the link in the description box. You will find out the solution for damped vibration. The second part is the steady part. Now we are going to find out the solution for the steady part, which is due to the influence of external periodic force. Let the second part we have written y2. So y2, let the solution is a sine pt minus theta, where a is nothing but the amplitude of that solution and p is nothing but the wave equation we have seen on the right hand side of the wave equation, f naught sine pt. Similarly, here also we have written p. So p is nothing but here the frequency of external periodic force. Now you can find out the single derivative d by dt of y2, which will be a p cos pt minus theta. Again, if you find out double derivative, this will be like a, here you can see cos theta, derivative will be minus sin theta, so a negative sign will be there, sin pt minus theta, another p will be there, so this will be p square. So we have the expressions for y2. For the y2 means the solution of steady part, its single derivative, its double derivative. Our aim is to here find out the solution, because there are two unknown quantity, one is a and one is theta. These two are the unknown quantity. We can find out a and theta by using all these values in the given equation. Let's find out that solution. Once we put the solution, the wave equation is in the form of, let's find out the solution. The wave equation is d square by dt square, so which is nothing but minus a p square sine pt minus theta. Here you can see minus a p square sine pt minus theta. And then 2r dy by dt. So 2r dy by dt means a p cos pt minus theta plus omega naught square y is a sine pt minus theta, which is equal to f naught sine pt. Now we'll rearrange. Here you can see sine pt, and in the third term also sine pt minus theta. If we take common, this will be like a sine pt minus theta. If we take common, then we will have here in the last term omega naught square, and here we will find out p square, plus the second term is 2RAP cos pt minus theta. And on right hand side we can rearrange like this: sine pt minus theta plus theta. We just rearrange that equation because we have here sine pt. If we add theta, subtract theta, this value will be same. This is because on LHS all the terms are, whether it is sine term or whether it is a cos term, they are having the form of pt minus theta. In order to make the right hand side also in that form, we just rearrange it. So left hand side remains the same: a sine pt minus theta whole into omega naught square minus p square, plus this is 2RAP and cos pt minus theta. Here you can see on the right hand side we can rearrange now by using the formula sine a plus b. So I hope you remember that formula sine a plus b, which is equal to sine a into cos b plus cos a into sine b. We are going to use that formula. F naught is constant, so sine a means sine pt minus theta into cos b cos theta, plus f naught into sine b into cos a. So sine b is sine theta cos pt minus theta. So now all the terms on LHS and all the terms on RHS are in the form of an angle which is equal to pt minus theta, where p is the frequency, the angular frequency of the external periodic force. So always remember, when this type of equation will come, when trigonometry functions are there, then LHS is equal to RHS only when, this is the only condition, only when the coefficients of trigonometry functions on LHS must be equal to the coefficients of trigonometry function on RHS. For that reason, we can now equate the coefficients on both sides. Here one term you can see sine pt minus theta. So the coefficient of sine pt minus theta on LHS must be equal to the coefficient of sine pt minus theta on RHS. So if we equate, the coefficient will be on LHS equal to a, and here omega naught square minus p square. On RHS you can see we have f naught and cos theta. So this is equal to f naught cos theta. And if we compare the coefficient of cos pt minus theta, we will have this equation like 2RAP equal to, on right hand side we have this much, f naught sine theta. Now we have this equation number 3 and equation number 4. Hope you understand. We just equated the coefficients of sine pt minus theta on both sides and coefficient of cos pt minus theta on both sides. We get this equation. So we will find out the solution now to calculate a as well as theta. So if we square and add, in next case you can see, if we square and add, here you can see a omega naught square p square and this much, this is, if we divide equation 4 by equation 3, if we divide, this will be 2RAP divided by this term, 2RAP divided by this term, a omega naught square minus p square, a omega naught square minus p square equal to, this is f naught sine theta divided by f naught cos theta. So here we just divided equation number 4 by equation number 3. Again you can see here equation number 4 by equation 3, f naught sine theta by f naught cos theta, 2RAP divided by this term. So here you can see a we can cancel, so 2RP equal to omega naught square minus p square equal to tan theta. So theta is nothing but tan inverse this term 2rp divided by omega naught square minus p square. So out of two unknown quantities, because we have considered that solution y2 as a sine pt minus theta, where a is unknown, theta is also known. So we get the expression for theta. Now our aim is to calculate a. So if we see here, equation number 3 and 4, if you see, if we square both sides and r, then we will find out the expression for a. So if see, remember, if we square and r, this will be a square omega naught square minus p square plus 4r square p square a square equal to, on right hand side it will be like f naught square sine square theta and f naught square cos square theta. So this is the solution you get if we add both equation 3 and 4 by squaring. On LHS we can take common a square, so the remaining part will be 4r square p square plus omega naught square minus p square whole square equal to, here if you take f naught square common, sine square theta plus cos square theta is 1, you can directly write. So this will be a square equal to, we have to just divide f naught square divided by 4r square p square plus omega naught square minus p square whole square, and a will be just square root of this term, so this will be f naught divided by that square root term, so 4r square p square plus omega naught square minus p square whole square. So this is the expression for amplitude of forced vibration. So what we have calculated here is that the expression we used y2 equal to a sine pt minus theta. So once we calculated theta and second we calculated now a. So we have the solution in the form of y2 equal to, we can directly write f naught divided by square root of omega naught square minus p square whole square plus that 4r square p square, 4r square p square sine pt minus theta. So this is our next equation. Clear? So we get y2, this is the solution of steady part, and here we have written the solution of the transient part. We have two different solutions here, one is for transient part, one is for steady part. So the most general solution will be in the form of y equal to y1 plus y2, where y1 is nothing but the solution of the transient part, that damped harmonic part, which is equal to a naught e to the minus rt sine omega t plus phi, and this is the solution for the steady part, which is equal to a sine pt minus theta. So this is equation number next, that 6 or 7 whatever you can write. So this is the general solution of forced vibration, which has two parts, one is for transient part, one is for the steady part. Always remember this transient part exists for a short period of time, but this part, the steady part, exists for a longer period of time due to the influence of external periodic force. So this is the most general solution, and we get the expression for a as f naught omega naught square minus p square plus whole square plus 4r square p square square root. So where amplitude is this much, and theta also we get already that tan inverse. So this is the solution of forced vibration. There are different cases of forced vibration also. One out of them is the resonance, where amplitude value will be maximum in that condition. In next video we will discuss about resonance, different applications of resonance in day-to-day life, whether resonance is destructive or whether resonance is constructive. We will discuss about in details about the resonance in the next video. So thank you.